going to discuss about Ampere's circuital law. Ampere's circuital law in magnetism is analogous to Gauss's law in electrostatics. We have studied Gauss's law in electrostatics in the first chapter, and this one is used in Ampere's, that is magnetism, and both are analogous to each other. This law is also used to calculate the magnetic field due to any given current distribution. We know Gauss's law is used to calculate due to a charge distribution. Similarly, the Ampere's circuital law is used to find or to calculate the magnetic field due to any given current distribution. And this is the statement of Ampere's circuital law. Ampere's circuital law states that the line integral of magnetic field induction vector B around any closed path in vacuum is equal to mu0 times the total current threading the closed path. That is, closed integral B dot dl is equal to mu0 I enclosed. Here B and dl are shown in bold letters because they are vectors. Where I enclosed is the current through the surface enclosed by the loop. This result is independent of the size and shape of the closed curve enclosing a current. This is known as Ampere's circuital law. Now let us define what is Amperian loop. Ampere's circuital law uses Amperian loop to find magnetic field in a region. That is, in the case of Gauss's law, we are using Gaussian surface now to find the electric field. Similarly, while we apply Ampere's law, we can use Amperian loop, and the Amperian loop is one such that at each point of the loop either B is tangential to the loop and is a non-zero constant, or B is normal to the loop, or B vanishes, where B is the induced magnetic field. Next, applications of Ampere's law. The first application is magnetic induction due to a long current carrying wire. Consider a long straight conductor Z is along Z axis. Let I be the current flowing in the direction as shown in the figure. Figure is shown here. The magnetic field is produced around the conductor. The magnetic lines of force are concentric circles in the xy plane because the conductor is kept in Z direction as shown by dotted lines. Let the magnitude of the magnetic field induction produced at a point P at a distance r from the conductor is B. Therefore, this is the figure. The green color shows a conductor in Z axis, along Z axis, and a current I is flowing through it in upward direction. Then you can see the magnetic field will be there around it in the shape of concentric circles. You know how you can find the direction of the magnetic field. You can use your right hand rule, that is, stretch the thumb of your right hand in the direction of current, then curl other fingers around it, around the conductor. Then the curling fingers will give you the direction of the magnetic field. In such way, we can find the magnetic field lines here, and it is marked as circles here, that is that black color circle. Suppose we are going to find the magnetic field at the point P, then we are going to apply Ampere's law. To apply Ampere's law, first we have to draw an Amperian loop including the point P. Therefore, we have selected a circular Amperian loop that is drawn in blue color, and it includes the point P, and the distance of the point P from the conductor is r. And suppose at the point P the magnetic field is B, vector B. Now you consider a small element of the Amperian loop, that is dl, vector dl, and you know the direction of dl we can find drawing a tangent there. Therefore, it's shown that the direction of dl is shown there by drawing a tangent. Moreover, you know the direction of the magnetic field around the circle is in concentric circles. Therefore, at that point the direction of magnetic field also will be in the direction of tangent. Therefore, both B and dl will be having the same direction, that is along the tangent. Now, according to Ampere's law, closed integral vector b dot vector dl is equal to mu 0 I enclosed. The direction of b at every point is along the tangent to the circle. Consider a small element dl of the circle of radius r at p. The direction of vector b and vector dl are the same. Therefore, the angle between them is 0. That is, closed integral vector b dot vector dl is equal to closed integral b dl cos 0 is equal to b integral dl is equal to b into 2 pi r, where integral dl is equal to 2 pi r equal to circumference of the circle, and I enclosed is equal to I. Therefore, from the Ampere's law, we can write b into 2 pi r is equal to mu 0 I, or b is equal to mu 0 I divided by 2 pi r equal to mu 0 2 I divided by 2 pi r. As mu 0 and 2 pi everything are constants, we can write b is directly proportional to current I and b is inversely proportional to the distance r. Therefore, if you plot a graph there between b and r, we will get a graph like this. Next, the equation implies that the field at every point on a circle of radius r is same in magnitude. In other words, the magnetic field possesses what is called a cylindrical symmetry, because at the same distance, that is at the same value of r, b magnetic field b also will be same. Therefore, we can say the magnetic field possesses cylindrical symmetry. The field direction at any point on the circle is tangential to it. Thus, the lines of constant magnitude of magnetic field form concentric circles. These lines called magnetic field lines form closed loops.